This next segment will deal with tests that are from data with only categorical values. So any information will be in the form of proportions. We'll cover 4 tests and start here with the proportion test. This is when you have a single categorical value, say gender, with 2 groups, male and female, and you want to know if the proportions of certain values differ from some constant. These are in the form of binomial, so yes, no, 0, 1, etc. We have an example down here. We asked if there's a significant difference in cancer prevalence of middle-aged women who have a sister with breast cancer compared to the general population. So we have one proportion comparing to a constant proportion. To do this kind of test in G-Power, we'll need to select from the exact test family, select proportion different from constant. This is also known as a binomial test. A priori, as usual, we're back to 1 and 2 tails like in the t-tests. We'll need alpha and power, and then the constant proportion. So that's whatever constant proportion you're measuring against. Then we'll hit determine. We'll need to enter the difference in proportion 2 and 1. And you can do the calc P2 from option. It really doesn't matter which one you do. They give about the same effect size, but this is what I would suggest. To do this, you get the constant proportion in the P1, so P1's constant, and then the alternative proportion is the P2. That's what you do for the background. If you're naive, you don't enter proportions at all, you just calculate the value of effect size, and it's 0.2, 0.5, and 0.8 for the exact tests. You want to sync your values and then calculate and transfer to the main window to get total sample size. Turning to our example question, is there a significant difference in cancer prevalence of middle-aged women who have a sister with breast cancer compared to just the general female population prevalence, which is 2%? We find that our null would be there is no difference, whereas the alternative there is a difference. So we already know that there's information here. Background on this proportion of cancer prevalence for women with breast cancer, it's 0.05. So we can enter the P2 there, the P1 there. We can sync the values. And once again, we're doing the difference P2 minus P1 for the options to get an effect size G of 0.03. And we're going to use 2-tailed because we don't care about the direction, just if there's a difference. And our constant proportion, of course, was that 0.02. We get a total sample size of 272. Here are 2 practice examples. I suggest, as in the previous segments, for you to pause this module and try these yourself before continuing on to the answers. This is on male incidence rate of cancer and female incidence rate of cancer. For number 1, we have the proportions, so we can enter the difference, which gives us a constant proportion of 0.0049, which gives it a very small effect size. And since we're interested in whether it's higher than the US average, we use a 1-tailed t-test, giving a whopping sample size of over 12 million. For number 2, we don't have anything about the female incidence rate. So we're going to guess a very small effect size and to get a constant proportion of 0.0042. One-tailed test gives us a smaller but still large sample size of over 2 million. Next, let's take a look at the Fisher's exact test. This is similar to the proportion test, but now you're looking at the difference between groups when the groups are not related. So instead of a group proportion against a constant, it's two different group proportions. It's also known as a independent chi-squared test. So an example might be is the expected proportion of students that pass in a psychology teacher stats course is that difference from the one taught by mathematics. In G-Power, we'll need to select proportion inequality to independent groups based under the exact test family. Tails, enter proportions, where P1 is the expected value, P2 is the observed value. And here, as in our way back when we did the 2-sample t-test, we can, in addition to alpha and power, we need to enter an allocation ratio. And this will be 1 unless the group sizes are different. We can calculate and get total sample size. For our example, is the expected proportion of students passing a stats course taught by psychology teachers of 0.85, so 85%, different from one by math of 0.95, 95%. So the null is that there's no difference in the proportion, and the alternative there is a difference. So P1 was our expected, P2 is observed, which we'll add in here. Only we want two-tailed because we only care if there's a difference, not directionality. And the group sizes we're assuming to be the same, which gives us a total sample size of 302 we need to detect this. Here are two practice examples for this Fisher's exact test. Pause now and try these on your own before continuing. For example 1, we have raw data, and we're asking if there's a difference. We see here, of course, that these are not numbers, but binary data, yes, no, proportions. So we can calculate the proportions ourselves. For psychology, the number of yeses was 7 out of 10. So yes mean pass, or 70%, while the biology proportion was only 60%. And given that twice as many students take the psychology class, our allocation ratio is 0.5. So that's going to 1 biology student for every 2 psychology students. We'll run a 2-sample test because we care about a difference to get a total sample size of 812, and since the allocation ratio was not 1, we get different numbers for biology and psychology. Now for the second question, we don't have any information on female students. We're just looking at the observed proportion of males. So we'll guess for females that maybe it's going to be 10% higher, so their expected value is going to be 0.85. We're going to select yes on a question. We'll use a one-tailed test because we think we're interested in higher to get a total sample size of 430, since we just didn't have different group sizes. It's going to be 215 each for males and for females. Moving right along, let's next examine McNemar's test, which is when you have two categorical variables and you want to know proportions, but these groups are related. So it's like the Fisher's exact test, but for paired data. This is also known as the dependent chi-squared test, as opposed to the independent chi-squared. So maybe you have interest in looking at the difference in innate immune responses, so good or poor, in patients taking vitamin D or not, yes or no. Do this in G-power, it's proportion inequality to dependent groups, so McNemar. You'll need to select one or two tails, and then an odds ratio, which we'll look at on the next page. So alpha and power as normal, and then we'll need the proportion of discordant pairs, which we'll look at on the next page as well, and calculate and get total sample size. To calculate odds ratio and proportion of discordant pairs, we have to understand what our data looks like for a McNemar's test. So I have trial data from our examples, 4 different proportions for each category pair of either good or poor response in the presence of vitamin D or no vitamin D. Now, the proportions have to sum up to 1, and we see that they do, 70%, 85%, and then 98 and 1. So the discordant pairs I've shown here, this pair and this pair, are the proportions for the group that don't match up. So the bottom one here is the good response for vitamin D and poor response for no vitamin D. While this one up here is poor response for vitamin D and good response for no vitamin D. The stronger these two categories are related to each other, the smaller the discordant pair proportions should be. So you see that these two are smaller than the other proportions. Now, once you know what the discordant pairs are, you can get the odds ratio, which is just the quotient, or dividing one by the other. So in this example, it's 0.02 divided by 0.13, which gives us 0.1538. Now, the opposite quotient produces the same result in G-power. So it really doesn't matter which way you divide them. I usually divide them just so that it's a decimal rather than a larger number. And then the proportion of discordant pairs is just the sum, so 0.02, 0.13. So that's how you get those two important metrics, those two important parameters. Taking a look at our example, if there's a difference in innate immune response, patients taking vitamin D or not, the null is there is no difference, the alternative is there is a difference. We have that background information we had from the last page. So the discordant pairs were 0.02, that proportion, and the other pair proportion was 0.13. The quotient gives us the odd ratio, and then the sum gives us the proportion of discordant pairs. We can enter those here and here respectively. We'll use a two-tailed test because we care about a difference. Give us a sample size of 100. Here are some practice examples. For the first, we already have that table of proportions. So we can pull out those discordant pairs being here to get the odds ratio of 0.8, and a proportion of discordant pairs is 0.18. We're interested in difference, so it's two-tailed for a total sample size of 3,562. For the second question, we have the raw data in yes and no, which we can use to get the table. I have here fractions, but of course we can use decimals. So that'd be first discordant pair is 0.2, the second is 0.3. So the odds ratio of those discordant pairs is 0.667, and then the proportion of discordant pairs is 0.5. Two-tailed, because we're interested in difference, to a total sample size of 398. Finally, we have the goodness of fit test. This is an extension of chi-squared test, which asks if a table of observed values are any difference from a table of expected ones. So more than true members in a group. While G-Power called this goodness of fit test, this is more generically called a chi-squared. A great example of this is looking at observed proportions of phenotypes in a genetics setting from the expected ratios. To do this in G-Power, we need the X-squared or chi-squared test family, and then goodness of fit, and then contingency tables. We'll enter, as usual, alpha and power, and then degrees of freedom, which is going to be your number of categories minus 1. If you have background information, you can enter the number of cells that equals the number of proportions. So the expected go in the null hypothesis column, while the observed goes into the alternative, or H1. And then if you have counts, you can just add the counts raw and then normalize them. Or if you have the proportions already, just enter them as proportions. Calculate and transfer to get total sample size. Naive, same 3 steps above, and then just estimate effect size. Let's look at that genotype example. Does the observed proportion of phenotypes from a genetics experiment, is it different from the expected 9 to 3 to 3 to 1? So the null is that there is no difference from the expected, while the alternative is there is a difference. So we're going to take our observed proportion to be the ratio of 9 to 3 to 4 to 0, or just 9 to 3 to 4. Our degrees of freedom is going to be the number of groups, or number of cells, so 4, because 1, 2, 3, and 4, minus 1, so 3. So we'll enter 3 there. Then going into our determine, we're going to add here, right now, since these are counts, we'll add in our null 9 to 3 to 3 to 1, and then our observed 9 to 3 to 4 to 0. And if we have, we normalize them by hitting this and this, notice how there's a change from counts to proportions. Then we can calculate, get our effect size for a total sample size of 131 samples. Here are 2 practice examples for goodness of fit. Take some time to do these yourself. The first example, we're already given the proportions. So we can plug those into the table, and we get an effect size of 1.04, and we have 4 different groups, ethnic groups. So that gives us a degrees of freedom of 4 minus 1, 3, so a total sample size of 10. For the second one, we're giving the raw data, looking at the proportions, and if there are any difference from essentially equal, 1 to 1 to 1 to 1. So getting these proportions, we get 7 out of 20 for freshmen, 5 out of 20 for sophomores, 5 out of 20 for juniors, and then 3 out of 20 for seniors, of 0.35 to 0.25 to 0.25 to 0.15. Plugging these in to those proportion tables, we get an effect size of 0.28, and since there's 4 different groups, degrees of freedom of 3 for a total sample size of 137. This concludes the segment on proportion or categorical variable only tests. We will finish up in the last module with linear regression and ANCOVA. Thank you.